welcome back to another edition of Chem Talks. Mr. J here. Today we are going to talk about some additional properties of solutions. Specifically, we're going to talk about solubility. So let's go ahead and get started. First thing, we can define solubility as the amount of solute that will dissolve in a specific solvent under given conditions. Remember, solute, generally we think of it as a solid in a solution, and their solvent is what's doing dissolving. Now remember, solute can also be a gas, it could be a liquid as well, but generally we think about it as a solid dissolving in a liquid. Okay, so how many grams can dissolve in a specific amount of water, let's say, since water is universal. The important part here is under given conditions, because the solubility will change based on a few factors. And there's three factors that we're going to talk about to start with today. First one is the nature of the solute and solvent. Second thing we're going to talk about that affects solubility is temperature. And then finally, a special case, we're going to talk about how pressure can affect gases. So let's look at the nature of the solute and solvent first of all. When we talk about solubility, we talk about things dissolving. We talk about the idea of likes dissolve likes. And what this means is that a solvent is going to dissolve best in a solvent that has similar chemical structure to itself. What do we mean by similar chemical structure? Well, we're talking about polar versus nonpolar molecules. If you remember, a polar molecule is one in which there is an unequal sharing of electrons. Electrons tend to hang out by the more negative atom and give it a slightly negative side, while the other side has its negative, or its electrons pulled away and has a slightly positive charge. Overall, the whole molecule is neutral, but it does have a slightly positive, slightly negative side. In nonpolar, what we see is there's an equal sharing of the electrons. So what we see is that polar solutes will dissolve in polar solvents, like dissolve likes. A good example of this is methanol, which is a type of alcohol dissolving in water. And then just the opposite is true. Nonpolar solutes are going to dissolve in nonpolar solvents. A good example of this maybe you've done is paint and clean paintbrushes. You use a turpentine. You don't, especially oil-based. You're not going to use water. It's not going to get them clean because water is polar, oil is nonpolar. So we're going to use nonpolar turpentine to do nonpolar paint as well. Okay, the next factor that affects solubility we're going to talk about is temperature. And we're going to look at this in a couple different phases. We're going to look at a gas dissolving in a liquid first. What we see is as the temperature of the liquid increases, the solubility is going to decrease. We can see that cold holds less solute. So temperature goes up, we can hold more. Temperature comes down, we can hold less gas in a given solvent. Why is this? Well, as we increase the temperature, we're also increasing the kinetic energy of the molecules of the solute. And as we increase those energy, they have a tendency to escape from the solvent, meaning they're going to be less likely to be soluble in there. A good example of this, if we look at dissolved oxygen in our streams, especially here in Colorado. Trout like really cold streams because they have really high oxygen. Sometimes if we have a drought year and our streams start to dry up, we get really worried because with less water coming in, the temperature of the sun raises the temperature of the water and it can hold less oxygen. Well, the trout need a lot of oxygen in order to survive. So at times I've actually seen them up in Yellowstone National Park ban fishing from the park because the water got so low that they were worried about the health of the trout. Another example of this is carbonated sodas. Okay, what we see is that a warm soda is going to hold less, actually will hold more carbon dioxide than a cold one. We'll talk a little bit more about that in just a little bit. If we look at solids dissolving in liquids, what we see with this case is just like we talked about before. If we increase the temperature, we're going to increase the solubility of it. This is an example of a solubility chart for various salts. Remember, salts are just an ionic compound. And as you can see in most all these cases, except for this one down here, as we increase the temperature down here along the bottom, the solubility, or the amount of solute that can hold, increases. Okay, not always the case, but in general we can see that's the general trend. Now if we look at pressure, okay, pressure, remember we said has to do with gases. And the solubility of liquids and gases, solids and liquids aren't going to be affected by pressure. But what we see is the solubility of gases and liquids is. Okay? So what we see is if we increase the pressure, more pressure, we're going to increase the solubility, which means as we increase pressure, we have more gas being dissolved into the liquid. It increases the number of gas molecules that are entering the liquid. What this is what we call Henry's Law. Henry's Law states the solubility of a gas in a liquid is directly proportional to the pressure of the gas above the liquid. Okay? So if we decrease the pressure, we decrease the solubility. Increase the pressure, we increase the solubility. Good example of this is a can of soda, like this Coke here. Think about it. You have a can, you shake it up a little bit. What happens as soon as you crack it open? First thing you hear is that sound. Well, that is the pressure from inside, which is relatively high, being released. Well, what's the next thing that happens? It starts bubbling. Well, what's causing the bubbles? It's effervescence from that carbon dioxide, the carbonation of it leaving. Okay, so as we open the pressure, we open the can, we're equalizing the pressure between inside the can and outside. We're decreasing the pressure above the liquid. Decrease the pressure means it's less solid, means that carbon dioxide that's trapped inside starts gushing out and it sprays everywhere. Another good example of this is scuba diving. I know we all know what scuba diving is. How many of you actually know what it stands for? SCUBA stands for Self-Contained Underwater Breathing Apparatus. First pioneered by Jacques Cousteau, if you know who he is. But there's a lot of solubility that's really important when diving. You spend a lot of time on this if you take a scuba class on understanding this. We've all seen that water is more dense than air. Think about if you walk down 10 feet. You're not going to notice difference. But if you jump into a swimming pool and sit at the bottom of it, you're going to notice a bigger pressure. So there's a greater pressure change in water than there is in air. In fact, at the surface, water we generally consider to be about 1 atmosphere pressure. For every 10 meters, about every 30 feet you go down, you're going to increase by 1 atmosphere. Like I said, you drop down and sit at the bottom of a 10-foot swimming pool, you're going to feel that pressure building up in your ears already. Well, this has a big effect on scuba divers. What it tells us is that at higher pressure, meaning the deeper we go, our bodies are going to absorb more gases. Okay, so as a diver goes down, where are we absorbing these? Well, we're absorbing it into our tissues, and that can lead to some problems. Okay, and as we come up, as scuba diver comes up, we're going to decrease the pressure, and that means that gas that was in our tissue is going to come out of it. Okay. As we're breathing in oxygen, we breathe in the scuba air. It's not just oxygen, nitrogen, hydrogen. Okay. Well, the oxygen gets put into our bodies, and it's being used up through cellular respiration. Okay. But the nitrogen is inert; it doesn't react. So what ends up happening with that is it gets what we call packed into our tissues. It just gets pushed into our cells. The deeper the diver goes, the more this nitrogen is packing into them. Eventually, what we see is we get an equilibrium. Okay, there's some coming in, some coming out. And it's not the nitrogen itself that is a problem, or that packing in. It's when the diver starts coming back up to the surface that we see a problem. So as the diver goes back up to the surface, the pressure is decreasing, meaning the nitrogen is now less soluble. So it starts coming out of the tissues because it's not being used up like the oxygen in cellular respiration. If you come up too fast when you're scuba diving, all of a sudden all this nitrogen that's packed into your body is released. It comes out just like the bubbles when we open the can of soda. And this is known as decompression sickness or the bends. This can be a really serious problem. The bends can be anything from joint pain to rashes to paralysis, which means you can't move. And if it's severe enough, it can lead to death. So scuba divers have to be real careful. And so what they do to avoid this, as they're coming up, they monitor their depth, and they limit the amount of time that they're at certain levels. If you go down, the farther deep you go, the less time you have on there. And what they do is as they come back up, they're going to slowly ascend. And they'll come up maybe 10 feet, 15 feet. They'll rest at that point for a minute or two. And then they'll go up again another 10, 15 feet and rest. And what they're doing at those rest stops is allowing the nitrogen to slowly dissolve or to come out of those tissues. Now, if you come up too quickly, that's when we have lots of problems. Okay, next thing I want to talk about is rate of dissolving. So we talk about solubility, we talk about things dissolving in a liquid. Well, rate of dissolving simply tells us the rate at which a solvent dissolves in a solution. And it depends on three factors: the surface area of the solvent, surface area of the solute, how much stirring dissolved, and finally temperature. So let's take a look at all three of those things. What we see, think of if you've ever seen the Alka-Seltzer tablets, plop, plop, fizz, fizz. Well, when we look at those tablets going in water, where do we see them dissolving? Is it from the inside or is it from the outside? Well, it's from the outside. So dissolving of a solute occurs on the outside of the first. It's going to work its way in. And so if we can increase that surface area, we get it dissolving quicker, which gives it a faster rate. So if we increase the surface area, we increase the rate of dissolving. Maybe you've seen some people crush up aspirin when they take it. What's that do? Well, increase the surface area. When it gets in their stomach, it's going to dissolve quicker and get in the bloodstream. The second factor involved in determining the rate of dissolving is stirring. So as we stir a solute, once it's put in a solvent, what's going to happen is that's going to prevent those clumps from sticking together. Well, if they don't stick together, we're going to get increased surface area, and as we just learned, if we increase the surface area, we're going to get a faster rate. So if we increase stirring, it's going to increase the rate of dissolving. And then finally, the last factor that affects us is temperature. And so if we increase the temperature, it's causing the particles to move faster. Well, if they're moving faster, they're going to come into contact between solute and solvent at a greater rate. Well, if they're coming at a greater rate, then that means it's going to dissolve much quicker. So if we increase the solvent particles, okay, the energy to move particles from the solid solute increases. So increasing temperature means we're going to also increase the rate of dissolving. Okay, one last thing I want to talk about, and that's what we call a saturated solution. Picture making Kool-Aid. I know a lot of us make Kool-Aid. How do you make it? Well, let's make it from the packet, right? You rip your packet open, you pour it in your container, you're gonna with water, right? And then you add sugar. If you read the directions, it said add 1 cup of sugar. So we add 1 cup of sugar, stir it in. But we all know if 1 cup is good, 2 cups must be better, right? So we add another cup, make it sugar. If 2 cups is good, 3 must be even better. So you add a 3rd cup and you start stirring, and all of a sudden you notice not all that sugar is dissolving anymore. Some of it just clumps up at the bottom. In that case, what we have is what we call a saturated solution. So a saturated solution is a solution which contains as much solute, in our example sugar, as can be possibly dissolved under existing conditions. So for a given volume or for a given pressure and temperature. So if we add any more solute to it at that saturated point, it's not going to dissolve. It's just ends up clumping up on the bottom, kind of like we saw when we added that 3rd cup of sugar to our Kool-Aid. Now, what we can do with that Kool-Aid, though, if we were to pour it in a pan and we heat it up, we can form what's called a supersaturated solution. A supersaturated solution is a solution that contains a greater amount of solute than is needed to form a saturated. So it's having more of that sugar in there. And the thing to know about these is they're very unstable. They don't remain supersaturated. So if we disturb them, all of a sudden what we can see is that all that extra sugar is going to come out of solution and forming back up on the bottom as a solid. And I'm going to show you a video of this in class for some neat chemicals that do this. So here's our example. In an unsaturated solution, we can add, let's say it's just sugar. So we're adding it, it's going to dissolve. Once we hit that saturated point, any additional solute we add is going to kind of form up on the bottom. And then if we heat it up, we can actually make this supersaturated. And then if I were just to get it supersaturated, if I add 1 little crystal to this, what we're going to see is all that solute that was in there, extra solute, comes out of solution and starts forming these crystals. Like I said, I'm going to show you a video on this. Today we talked about a couple things. First, I talked about solubility. How much solute can dissolve in a given amount of solvent, and the factors that affect it. We talked about how those 3 factors that affect it, and then we talked about dissolving, and we also talked about applications of Henry's Law. So if you have any questions, guys, as always, please come talk to me before class. Otherwise, we'll see you in class.